like when you think, okay, well, what line is going to fit the data well? You kind of eyeball it, right? So it's going to be like probably something that looks roughly like this. So certainly that line is going to fit the data better than, say, a line that has a downward slope like that, or even just a straight line that went through like that. But once you get into sort of lines that have approximately this slope and approximately this intercept, it's not totally clear which one is going to be the best fitting. So when we describe, or when we talk about having the best fit, what we're talking about is looking at the deviations between the actual line that you plot and the data points themselves. So you can see that basically the line is providing a better fit for some of the data points than for others, right? So for example, for this data point, you can see that the difference between the value of y, so let's just say that we're getting a case where we're looking at these hospitalization and air pollution data. So the number of hospitalizations that's predicted by the line is substantially different than the actual number of hospitalizations that you observe on that particular day, right? So for this data point, the line does not provide like the greatest prediction. Same thing for that one. Just relocate some of these. Same thing for that one. But for other ones, you can see that it's almost perfectly on the money. So for this one, it came very close to predicting the actual number of hospitalizations. Ditto for this one, and ditto for that one, right? So, for some of the points, the line is doing better, and for other points, it's doing worse. Now you can think about like shifting the line around to try to end up fitting some of these points better, but there's always going to be a trade-off, right? So if we shifted the line down, then we'd end up getting a better fit for that point and for that point. We'd end up getting a much worse fit for say that point and that point, and we'd also end up getting worse fits for that one and that one, probably that one too if we shifted it down enough, right? So there's always a trade-off here, and what the linear regression is doing is basically trying to balance that trade-off and find the line that ends up fitting best on average. So in order to define what we mean by best on average, what it does is it takes all of the deviations between the deviation between each point in the line, and it squares those deviations. So you want to square them because if you didn't square them, then positive and negative deviations would just offset each other, right? So one thing you do is you think about, well, why don't I just take the sum of all of the deviations between each point in the line, sum those up, and try to minimize that sum to find the best fitting line, right? But if you did that, then essentially this positive deviation here would be offset by a negative deviation here, and so if you just had these two data points, you would think like, wow, I have a perfect fit or almost perfect fit because the sum of the two deviations would be close to zero. But in actuality, it's just one of them was too high relative to the line, and the other one, I guess this one your prediction was too low relative to the true data point, this one your prediction was too high relative to the true data point. So it's like there's some statistician joke or something where like three statisticians go hunting, they find a deer, the first one shoots y to the right, the second one shoots y to the left, and the third one says, oh, yeah, because on average they did, but in actuality, of course, the deer isn't harmed, which is good for the deer. So just doing the sum of the deviations clearly is not going to get you very far. Instead, what we do is we square these deviations. So instead of taking the sum of all these deviations, you take each deviation, you square it, and then you take the sum of the squared deviations. Once you square it, then of course we know anything squared has to be non-negative. So at that point, then positive and negative deviations cannot offset each other because they're both being squared. The side effect of doing the squaring is also that linear regression tends to try to minimize outliers. So like let's suppose that instead of this point being right here, that it was like all the way down here. So this would be a very large deviation, and then when you squared it, it would become even bigger. So if this data point were actually down here, the line would adjust substantially to try to not have such a large deviation for this single data point. Whether or not that's a good or bad thing is kind of it's a little bit subjective. Like there's not some strong theory that tells us yes, we want to take deviations and then we want to square them to really penalize these outliers. Obviously, you need to make the deviations non-negative for the reasons I described before, but you could think about instead of doing the sum of square deviations, you could instead do like sum of the absolute deviations and then try to just minimize that. It turns out that is a different type of regression. It's called median regression, and basically what it does is estimates how the median of y changes instead of the mean of y. But that's a topic for even I don't think even if you take econometrics, the undergrad econometrics course, you probably don't get into median regression. So for our purposes, we're just going to think about mean regression, which is where you try to minimize the sum of those square deviations between the line and the data point. Okay, so because of this, linear regression is also called ordinary least squares, or OLS, because what it's trying to do is it's taking the squares of all these deviations and then trying to minimize them. So that's the least part and the squared part. So if you actually solve this problem, it turns out that the linear regression slope coefficient, so that beta coefficient that I unfortunately erased, but so often I'll just write this. So e of y given x. So it turns out that when you solve this problem that I described up here in the figure, that beta is going to be equal to the covariance of x and y, which is the same thing as the covariance of y and x, divided by variance of x. And so you can actually solve that. It's not that difficult to do. But so let's assume that the expectation of y given x takes this linear form, so that it does actually look like alpha plus beta x. We can then write y as being equal to alpha plus beta xi plus ei or epsilon I. So epsilon I is just this, or ei is just this residual term, and it's just going to be defined basically tautologically to be the difference between the actual outcome yi and what your prediction of the outcome is, alpha plus beta xi. So in our graph, in the figure that I drew up here, this is the line alpha plus beta xi, xi, yi. I just indexing our observations, our data points, and of course this is going to be equal to, so this is the origin. So then that has to be equal to alpha because that's just the intercept. So each of these little deviations that I drew up here, those are the ei's. So this is like an ei here, this is one here, this is one here, for all of the different observations. So formally what OLS is going to solve is basically to minimize, with respect to alpha and beta, the sum of the square deviations between yi and our conditional expectation of y. So the actual yi and the conditional expectation of yi, which is equivalent to minimizing, with respect to alpha and beta, the sum of the square deviations between yi and alpha plus beta xi, because we said that the CF was equal to alpha plus beta xi. So if you solve this problem, what you will find is that, in fact, beta is equal to the sum over I of xi minus x bar times y minus y bar divided by the sum over I for the entire data set of xi minus x bar squared. So the definition of the covariance and the variance, so this is definitely these are two quantities you definitely should have seen any previous statistics course, but the definition of the covariance between x and y is this numerator divided by n. The definition of the variance of x is this denominator divided by n, and so this thing divided by this thing has to be equal to the covariance divided by the variance, because the divided by n's would of course just cancel each other out since they would appear in both the numerator and the denominator. Okay, so this is all being, we've solved this entire problem sort of assuming that the conditional expectation function has or is in fact linear. Potentially it could be nonlinear, so I could have drawn up instead a case in which, again, this will be like oversimplified relative to most real data sets, but let's just suppose that you had something like this where there was a very strong relationship between x and y that was like highly nonlinear. Okay, so you can see that if we were to try to come up with an estimate of the conditional expectation function here, it would be sort of steeply convex, right? It would start out with a relatively low slope, and then it goes up to a higher slope. So in that scenario, imposing the linearity assumption might not be all that palatable. So suppose that CF is in fact a nonlinear function of x. For example, in the example that I previously plotted as well, up on in the slides, it looked like it was nonlinear, although again I said that was deceptive because it's really just an artifact of the fact that we have very few data points out here in the over 5 range and maybe also in the less than 2 range. So in those scenarios, linear regression obviously it's not going to give you the true conditional expectation function because you're trying to fit a linear function to what's actually a nonlinear function, so you're not going to get it exactly right. That being said, it's still going to give you the best linear approximation to the nonlinear CEF. So the way to look at it is that regression is going to give you the straight line that most closely fits the curved CEF. Right? So the true CEF here looks like this curved line that I drew up. Linear regression is going to try to fit a straight line that approximates that curved line, so it would probably look something that's like closer to that. And frankly, that's not that bad. It'll be bad in like sort of some ranges of x. So like down here, obviously, it's severely overstating how much y tends to change as x changes because the actual slope we can see is pretty low, but the linear slope, the straight line here, has to have a pretty steep slope. And up here, it's going to somewhat like mildly understate the change in y that we should expect from a 1 unit change in x because the true CF is a little bit steeper. But overall, kind of I'd say like in this range, it's giving you a pretty good approximation to the actual CF. Furthermore, if you're just interested in like how closely the two lines are to each other rather than comparing the slopes of the lines, I would say it does even better. It's like pretty close throughout most of the range. So basically, the takeaway is, if you estimate a linear regression, you are imposing a linearity assumption on the conditional expectation function. But in most cases, there's not a big cost to doing that. So you can think of it as being good enough for most purposes, unless the CEF looks really weird. Particularly in this course, any regression you see, we're not going to really worry in general, I think, about whether or not the linearity assumption actually holds. That's like the least of our concerns when we're interpreting these regressions. So what we'll end up being much more concerned about is the following, which is causality. So what we mean there is whether or not we can actually ascribe a causal relationship to the conditional expectation function that we plot. Okay, so before we get into causality, I want to first emphasize that it's always going to be safe to apply what I would call a descriptive interpretation to a regression coefficient. So remember, the regression is just summarizing the conditional expectation function. So it's always going to be safe to say that if we observe that xi increases by 1 unit in our sample, then on average we expect yi to increase by about beta units. It's not going to be exactly beta units because again there is there's underlying variation in the data, and so you don't expect to always see the exact same response. But approximately, on average, we would think that y is going to increase by beta units. So in our example, what we're saying is that if we observe air pollution falling by 1 part per million in our data, then we would expect daily hospitalizations to fall by beta number of inpatient hospitalizations per day. However, that does not imply that beta represents the causal effect of reducing air pollution. For example, it doesn't necessarily imply that we would expect to see some sort of proportionate reduction if we were to some reduction, say, that's approximately equal to beta in the number of hospitalizations, if we were to impose a pollution tax that ultimately reduced the number or the average level of air pollution by 1 unit. And so you've been exposed to this many times before. Basically, the way that people describe it is correlation does not imply causation. So that's true. That correlation doesn't imply causation. That being said, it doesn't mean that that the regression is giving you a wrong answer as long as you don't try to ascribe a causal interpretation to it. Okay, so let me see where I want to go. So I think we'll basically stop there. So let me just describe like a case in which you could have a descriptive or predictive relationship that is valid if you interpret it correctly, but doesn't imply causality. So I think I remember seeing an article a few months ago that was talking about data that Facebook had collected on users, and in particular, they were trying to estimate like the relationship between whether users liked a specific candidate in elections. I think they're going back to like the 2012 elections or something like that. So we had like the number of likes for a candidate and the probability that that candidate won the election, right? And so they found that it was in fact predictive. So basically, candidates who attracted the most likes on Facebook were more likely to win the elections. It wasn't deterministic. It doesn't mean that if you have the most likes, you're sure to win the election. This means on average you're more likely to win it than a candidate who has fewer Facebook likes, right? And so they I don't know if they wrote a small paper about it or what, but they basically published their results somewhere either online or maybe in a journal or something like that. And so the article I read was actually criticizing it and saying like, well, this is stupid because we know that there's not, we know that this doesn't represent a causal relationship, right? It's not necessarily the case that, in fact, it's almost surely not the case that getting additional likes causes you to get elected. Rather, what it probably is telling you is that if you're a more popular candidate, then more people tend to like you and therefore will give you more Facebook likes. And so there's, sort of this omitted variable, which is your inherent popularity, that is correlated both with the number of likes you get and with the chance that you win the election. So it's true that relationship doesn't, that relationship between Facebook likes and whether or not you win the election is surely not a causal relationship. But that being said, it's still, a valid description of a valid summary, a sort of summary of the relationship between the two variables in their data. And second of all, it does have predictive power. All it's basically saying is like, look, we see that when you have a lot of likes on Facebook, then you're probably a better candidate, and therefore it would be reasonable to expect that you're more likely to win. So the criticism of the original article was actually misguided in the sense that, to the degree that, so I don't think in the original article, the original Facebook article, I don't think they were claiming that it was a causal relationship. I think they were basically just saying like, hey, this is something we found in our data, and potentially you could also, I guess, if you wanted to, you could kind of like use it as an additional predictive variable if you're trying to figure out which candidate was more likely to win. But they weren't saying that it had a causal relationship. So running a regression or estimating CEF between whether or not you win the election and number of Facebook likes is perfectly fine and valid as long as you just say, like, this is a descriptive relationship of what's going on in the data, and don't say that, if you go out and run some campaign and get an additional 1,000 Facebook likes, then we think that you have caused your chances of winning the election to rise by 10 percentage points or whatever. So basically the criticism article just applied this sort of thing of, like, correlation does not imply causation. That's true, but the original article wasn't trying to claim that the correlation did represent something causal, and so therefore the criticism was actually misguided in that sense. Okay, so we'll just stop there, and when we come back on Friday, we'll start talking about what it does actually mean to apply a causal interpretation. If you didn't turn in your problem set yet, drop it at the front here. Hi.